So, and this applies to bases as well. What makes a strong acid strong is the fact that it dissociates, which is just a fancy word for breaks apart, completely. In aqueous solution. Right? So that means if that acid breaks apart, we're going to get lots and lots of ions that are being produced. So for example, HCl, we mentioned HCl as being an example of a strong acid before. In solution, this is going to break apart completely. The H plus is going to be produced. That's going to grab a hold of the H2O to make H3O plus. Do you remember the name for this thing? That's the hydronium ion. And then we get the conjugate base of HCl, which is the Cl minus. So in solution, if you have a strong acid like HCl, all you have in there are these things, these ions floating around in the solution because it breaks apart completely. Right? That is what makes a strong acid strong. Its ability or the degree to which it breaks into ions. A weak acid, on the other hand, does not dissociate completely. It only breaks apart a very small percentage of the time, which means we're going to have a small amount of ions. And the way that you can tell really quickly from an equation that you're dealing with a strong versus a weak acid is the type of arrow that you see. Right? So if we're dealing with a weak acid or a weak base, the arrow actually looks different than a regular arrow. It actually goes in both directions, which we've seen before, but we didn't really talk a lot about it. So the arrow goes both ways. Right? So what this suggests is that our H2CO3, which is a weak acid, this is carbonic acid, in water, some of it breaks apart to give you the hydronium and then the conjugate base. But what also happens is these two things here react together to make the original compounds. So you don't have a bunch of this. You actually have a very, very small amount of ions present. So small amount of ions. And you have a larger amount of the undissociated acid. All right, and what's your clue, again, that one thing is strong versus weak is the type of arrow that you see. Right, if you see a regular arrow, that means it goes completely from the left side to the right side. If you see a double-headed arrow, that means it can go both ways, which we'll address here in the next section. All right, so the degree of dissociation makes something, an acid or a base, strong versus weak. All right, so just to kind of illustrate that point here again, if we have another strong acid, let's say like HI, right, in solution, in water, in aqueous solution, this is going to break apart completely, and all we're going to have there are a bunch of these ions floating around, right, the hydronium, and then we have the conjugate base of HI, which is I minus. You don't have any of the original acid here in the solution. It's completely broken down compared to a weak acid, which is very different. All right, so the strong acids we talked about, we listed 3 of them the last time, so let's revisit those. The 3 strong acids: hydrochloric acid, HCl, which is found in your stomach, by the way, stomach acid. There is H2SO4, which is sulfuric acid, and that's found in car batteries, battery acid. And then nitric acid, which is sort of the strongest out of those 3, right? So all 3 of those in solution, they're going to break apart into ions, and all you're going to have are H3O plus and the conjugate base. So and that's different than our weak acids, right? So in contrast to the strong acids, our weak acids such as HF, hydrofluoric acid, we dissolve this in water, just a small percentage of it is going to dissociate or break apart. And we get small amounts of these ions. In solution, we actually have a lot of the original undissociated acid left over. The arrow here, the double-headed arrow, is our clue that we're dealing with a weak acid. All right, and then the weak acids, again, the majority of the acids that you're going to encounter are weak ones, and out of those, there are several that are more common than others. And there are 3 also that we mentioned the last time, all right? So I'm not sure if you remember those, but they were phosphoric acid, H3PO4, which is often found in stuff like your soda, for instance. There is acetic acid, which is in vinegar. Vinegar is just a dilute solution of acetic acid. A lot of times when students first, learn the names, they mispronounce it as acidic acid. Right? It's not acidic, it's acetic. Right? Acids by definition are acidic, so it's not an acidic acid. And then carbonic acid, H2CO3, which is found in any carbonated beverage, right? So anything that has CO2 dissolved in it.
These are the same ones you gave us on Monday.
Those are the exact same ones.
Okay.
Yeah. We're just revisiting them again to show you now, which ones are strong, which ones are weak. All right. So we've seen how we can differentiate strong acids versus weak ones. It just has to do with the degree of dissociation. If something dissociates completely, it's a strong acid. If it doesn't dissociate as much, it's a weak acid. We can apply that same reasoning to our bases, right? So the strong bases, these are also going to dissociate completely. And one of the initial definitions of bases was the fact that they contain that hydroxide ion, right? So when they dissociate completely, we're going to get lots of the hydroxide ions and the cation as well in solution. So for example, we have potassium hydroxide in water. It's going to break apart completely. Our arrow here tells us that, right? So this is not going to stay together. It's going to break into its ions in solution. Same thing with, sodium hydroxide, which is even more common than potassium hydroxide. It's a strong base, so lots of ions. In solution. And then in contrast to that, right, you can kind of guess what's going to happen with the weak bases, right? These are not going to dissociate as well as the strong ones, and as a result, we're only going to get few ions, a very small amount of ions in solution. And again, our arrows here are going to indicate to us that it's weak. So for instance, ammonia, NH3, very common weak base. Right? You have that in stuff like your oven cleaner or your window cleaner at home. Those are all ammonia-based cleaning products. Those are weak bases. In solution, yes, they will dissociate, but very, very small percent of the time. Right? So this here, it's going to act as a base. It's going to accept that H plus from the water. We form the NH4 plus. We take away an H plus from the H2O. We end up with hydroxide. So it still produces hydroxide, but we only get a small amount of those ions in solution. So small amounts. Produced. So the ability of something to break down or to break apart into ions is what we're using as our guide for determining whether something is strong, whether an acid or base is strong versus weak. Okay, questions on strong versus weak acids and or bases. All right, so this idea of using that double-headed arrow to represent not a complete or an incomplete dissociation is going to be important, as we're going to use it now to address another characteristic or another phenomenon associated with acids and bases, which is this idea of equilibrium. All right, so equilibrium, which we will abbreviate as EQM, we're going to see these types of reactions, not just now, but eventually when we get into the second half of the semester, we're going to see other types of acid-base equilibrium reactions. Sometimes these are referred to as reversible. Reactions. And what does reversible suggest to you? You can undo it, or the reaction can go one way, and it can also go in the opposite way, right? So it can be reversed. So in an equilibrium reaction, there are two reactions occurring simultaneously. A forward, which by default goes from left to right whenever we write an equation. And we also have the opposite of that, which is the reverse reaction, which goes from right to left. Right? So normally when we write a reaction, we go left to right. What we're saying for a reversible reaction, we also have the opposite happening simultaneously. All right, so we'll pull back in the equation that we looked at previously to represent the weak acid HF. So in solution, we saw that HF with H2O, and we saw that double-headed arrow to produce our H3O plus and the conjugate base F minus. Right, so what this is telling you are actually a couple things. The first, right, which we just talked about, is that this suggests here that our acid is going to be weak. Right? The second thing is that this reaction occurs in both directions. So we have the forward reaction happening, where the HF and the H2O combine to produce H3O plus and F minus. Right? That's by default how we think about reactions from left to right. But what is also happening is the reverse. So the H3O plus and the F minus, the H3O plus and the F minus can combine to make H2O and HF, right? That's the reverse reaction that's occurring. So you have both of those happening at the same time, simultaneously. Right? And that's unusual, right? We haven't really talked about that when we looked at chemical reactions. We've always assumed that reactions go from left to right. That's not always the case, however, which is actually a very important and a very useful thing. So, what does equilibrium actually mean? So, when a system reaches equilibrium, the way that we determine that it has reached equilibrium is when the rate or the speed of the forward reaction is equal to the rate or the speed of the reverse reaction. All right, I'll give you an analogy to hopefully help illustrate this. So if you think about, if you've ever hopped on a treadmill, all right, and you turn the treadmill on and you set it to whatever, 5 miles an hour, and the treadmill starts to move that way, or the thing on the treadmill, the tread starts to move that way at a speed of 5 miles an hour. What do you have to do on that treadmill so you don't go flying off the treadmill? You have to walk that way at what speed? 5 miles an hour. Right? So your speed in that direction equals the treadmill speed in that direction. And as a result, person looking at you, it doesn't look like you're going anywhere. It looks like you're stationary. Even though you're moving your arms and you're moving your legs. Right? You're still doing stuff, but you're not going anywhere. Because the rate in one direction equals the rate in the other. The same thing that's happening in your chemical reactions when they establish equilibrium. The rate at which the products are made is the same rate at which the products are converted back to reactants. And what that suggests then, at equilibrium, the amount, so at equilibrium, the amount or the concentration, is a better term to use, the concentration of the products is constant because as they're made, they're being used back up. So the concentration doesn't change. And similarly, at equilibrium, the concentration of the reactants is constant or does not change. Right, so those are a couple of the hallmarks of systems that are at equilibrium. Equilibrium is established when the speed of the forward reaction equals the speed of the reverse reaction. And as a result of that, the amount of products that you have doesn't change. The amount of reactants that you have doesn't change either. You can apply that reasoning to any chemical system that is at equilibrium. It doesn't have to be acid-base equilibria. It could be other types of equilibria as well. So if you have a system at equilibrium and it gets disturbed somehow, what's going to happen? All right, so we'll go back to the analogy. You're at the gym, you're on the treadmill, you're at 5 miles an hour, you're not going anywhere, you're like a hamster on a wheel, right? Except you're on a treadmill. So you're moving, but you're not going anywhere, the treadmill's moving that way, you're watching the TV, following the coronavirus and whatnot. And somebody next to you, right, they sneak in and they increase the speed of the treadmill without you looking. So it goes up to 6, 7, 8, 9, maybe 10 miles an hour. So they've disturbed your equilibrium. How do you respond to that disturbance? You speed up as well, right? So they have perturbed your system and you responded in a way to re-establish a brand new equilibrium. Right? In that case, your response was to speed up as well. So something similar is going to happen with your chemical reactions when they get disturbed or perturbed. They will respond in such a way to minimize the effect of that disturbance, and as a result, establish a new equilibrium, and that is known, that idea is known as Le Chatelier's principle. So let me rewrite that in a maybe more user-friendly way. So for a system at equilibrium, and that's the key thing, right? It has to be at equilibrium to begin with. If disturbed, the equilibrium will respond, the system will respond in such a way to minimize the effect of the disturbance and as a result it will establish a new equilibrium. Okay, in a nutshell, that is what Le Chatelier's principle is, and you can apply it to all sorts of disturbances. It doesn't just have to be the two that we're going to be looking at today, but we're going to focus on those because those are the most common disturbances that we can do to a system that is at equilibrium to begin with. All right, so You're at equilibrium, you disturb it. How is the system going to respond to minimize the effect of that disturbance? Well, let's take a look at I'm just going to redraw this here so I can do it my way. All right, so let's say we have our same system at equilibrium, HF plus H2O. All right, there we have our double-headed arrow. We get the conjugate base, F minus, and we get H3O plus. Right, same equation we've seen several times already today. So, a couple of things to note. First thing is, it's an acid-base reaction. We have an acid, we have a base. Second thing to note is the arrow. Right, so the double-headed arrow is your clue that this is a reversible reaction. It's going to be a reaction where equilibrium is going to be important. So let's say we disturb this. And we're going to disturb it by adding HF. Right, so we're starting off with this thing at equilibrium, whatever that equilibrium is. It's nice and steady. And then we add some more HF to the system. How is the system going to respond to minimize the effect of that disturbance? In other words, if I add more HF to it, how will the system respond to get rid of the HF that I just added? What's the only way I can get rid of HF? If I add more of this stuff, the only way to get rid of it would be to convert it to the stuff on the right. Right? That's the only way to get rid of it. So if I add something here, the equilibrium is going to respond to get rid of it, to convert it to the stuff on the right. So we say that equilibrium shifts to the right. To minimize the amount of HF that I just added to the system. If I added H2O, hang on, change that. If I added F minus to the system, how will the system respond to get rid of the F minus? It'll shift to the left, right, to convert the F minus back into the HF. So the equilibrium here shifts to the left. So when you add something to a system at equilibrium, the equilibrium shifts in which direction? The opposite way, exactly. So if you add something to the left side, it's going to shift to the right. If you add something to the right side, it's going to shift to the left. That's how equilibria work. All right, what if I change the type of disturbance? Let's say now I removed HF. I take HF away. Take some of this away. How is the equilibrium going to respond to make some more HF, or to replace the HF that you took away?
Give it to it on the right.
It's going to shift to the left, right? So if you take something away, you make a hole here, in other words, right? You have to fill that hole back. The only way to fill it is to go that way, to make more of the stuff that you just took away. Right? So you take something away, the equilibrium shifts in that direction. So if we remove HF, the equilibrium is going to shift to the side where the HF was, which in this case is to the left side. Right? And then if we did the opposite, if we removed F minus from the right side, if we take F minus away, the equilibrium shifts to make more of it. It's going to shift to the right. So with a system that is at equilibrium, we can disturb it, we can perturb it by changing or by taking away a reactant or a product, or by adding more of a reactant or a product to force the equilibrium in one direction or another. So for example, right, if I wanted to make lots and lots and lots of F minus, right, that means I want my equilibrium to go that way. As I make F minus, I'm just going to remove it. And as I remove it, equilibrium shifts to make more of it. Take it away, it shifts to make more of it. Right? So you can actually tweak your system. You can control it by applying Le Chatelier's principle. Right? In this case, it's an acid-base reaction, but you can apply it to lots of really, really important reactions. There are other things we can do to disturb a system at equilibrium. We're going to limit ourselves in this class for just adjusting or affecting or disturbing the amount of the concentration of the reactant and products. Either add some more of something, equilibrium shifts in the other direction, or we take something away and it shifts back to that direction. Right? That's the main point of how we're going to apply Le Chatelier's principle.